Hello, and welcome to Ants Are Everywhere. This is our round 3 look into DeepSeek. So, last night I took a closer look at the V2 and V3 papers. The V3 paper, they call it a technical report. I think they call it a technical report because there's not a whole lot that's new here. And I think it probably makes sense to look most closely at the V2 paper. And I wanted to get to the code, and I only have about an hour. So I think we'll go kind of cut straight to the chase architecturally, and then take a look at what the code corresponding to that architecture looks like. For V3, it seems to me like the main additions. How do I pop this out here? Whoa. It seems like the main new things in V3 are there's some distillation from the R1 paper that we looked at yesterday. Knowledge distillation from DeepSeek R1. And then they made a few updates to pre-training, including a floating point 8 mixed precision training framework, basically training in lower precision floats. And they tweak their algorithms for running mixture of experts and load balancing. It's essentially parallelization of the DeepSeek V2 architecture. We do get this nice diagram where we see that there's a bunch of transformer blocks. They run RMS norm. I think this plus sign here means that they I forget what this is called, but they add back the original vector after applying attention to kind of recapture some of the information. And the attention heads use this multi-head latent attention, which they talk about in the V2 paper. And then there's some routing stuff. I'm not quite sure what a shared expert is, but they do this mixture of experts thing where they also have a bounded number of devices that will receive each token. But essentially, the model is distributed among experts, so different experts can run on different GPUs. And in fact, different layers also run on different GPUs, and that's essentially just a way to parallelize the model. And then you train each expert has its own there's an expert level loss function that trains the experts to different experts, and then there's a loss function that handles like the routing, and there's a couple more loss functions in there, but that's essentially all trained as part of the model. And this diagram, I'm not sure is the most easiest way to understand what the what do they call it, multi-head latent attention is. Let's see if we can find the V2 paper, which I opened somewhere. Certainly it's here. Maybe this is the only place it is. So the multi-head latent attention, which seems like the main architectural contribution here, is also looks really straightforward. So what they're doing, Hey, Friction. Good morning, or good morning my time. Hope you are well. I don't know where to put this when I'm reading PDFs. Let's put this just over to the side for now until I find the section I'm looking for. So the multi-head latent attention, they talk about the regular multi-head attention. You've got these queries, keys, and values, and I forget what H is. H is something like the input. H sub T is the attention input of the teeth token at an attention layer. Okay, and then these W super Q, W super K, W super V matrices are learned. And then the QT that they get from applying this matrix, they split into sub vectors. It will be sliced into n sub h heads. So these are the different attention heads. And then they run, the different heads essentially learn different things. And then they run this soft max where you take query ti dot product it with k ji. So we're running from j equals 1 to t. So t is the end of the iteration. I'm not really sure what I is doing. I think maybe I is just summing over this I, Einstein summation style. But at any rate, we take the q sub t and the k sub j stuff and essentially dot product them, divide out by the square root of d sub h, which I think is just a dimension. And we take the soft max of that, and then we multiply that by the value. So this is essentially the taking the key, kind of commingling it with a query and getting the value out somehow. And then we get this u sub t, which I think is the final output from this layer. We, again, apply a learned matrix to the output. I think in benchmark, it beat DeepSeek and O1. I think that's right. They talk about benchmarking of the MLA at the in one of the appendices. And so here's a model of, I guess, multi-head attention, and the I think the shaded area is what's cached during inference. So you cache all the keys and cache all the values. Those keys and values we know are really just like subcomponents of single vectors. And then for each query, you have the keys and the values, and these keys and values might be different. These are the grouped query attention and multi-query attention were other proposals for how to reduce the amount of caching. Grouped query attention, I haven't read the paper. It looks like they're basically just saying zip up these queries into tuples, and a tuple will share keys and values, and that will reduce the amount of caching by half. Multi-query attention, I don't know how this compares to like whatever the first attention model was, but basically you have different queries, but they all share keys and values, and that reduces the size of the cache by like the number of heads. And then what DeepSeek is doing, which seems really natural to me, I'm a little bit surprised that nobody else got there first, is they're just compressing the key value stuff. They're compressing keys and values, I think, as a single vector. And then they call this projection. Projection normally goes from the higher dimensional space to the lower dimensional space. But I think that what they're doing is they are taking this stuff, which is higher dimensional. It's got more bits than we want to have in our cache. They're reducing its dimensionality by projecting it down to a compressed space. And then during inference time, they take a learned matrix and decompress the compressed key value. Seems like all that they're doing. They talk about this here. Low rank key value joint compression. They say that C sub T super KV in R, this is just the dimension of the vector space, upper D sub C. So this thing here, CTKV, is the compressed latent vector for keys and values. This dimension is much smaller than the dimension of the, I guess, number of heads times the dimension of the head. I'm not sure exactly that's what those stand for, but at any rate, the point is it's much less than what we would have with ordinary multi-head attention. And this denotes the KV compression dimension. And the point here is it's just much smaller. And then WDKV here, they call the down projection matrix. So this is the matrix that compresses, I guess, the input. And WUK and WUV are the up projection matrices. I don't know what down projection and up projection are, but these are essentially, this is compression and this is, I guess, decompression. And so the main point is that during inference, MLA only needs to cache this CTKV. So its KV cache has only DC times L. I don't know what L is. Elements. Where L denotes the number of layers. Okay. So we've just reduced the size because we're compressing the key value cache, which makes sense. And they had to tweak the embedding to make that work. So they were using rotary position embedding. And they have to tweak it a little bit because if they had used it as is, just because of the way matrix multiplication works, they wouldn't be able to do one of the tricks they do to get even more compression. Essentially, they combine two learned matrices into one, as opposed to learning them separately. And in order to make that work with rotary position encoding, they have to do some tricks. It's not a hard trick. I forget exactly what they do, but we're just going to kind of gloss over it for now. Or maybe not. So they propose a decoupled rope strategy that uses additional multi-head queries, and a shared key to carry rope. So I think that, so we have additional queries and we have a shared key. And so I guess we're kind of like learning the rope stuff. We do call rope on some matrix times the whatever CTQ is. I think CTQ is different from what we had up here, right? It's some compressed, I guess, query stuff and getting some Ks. And then the shared key is KT super R, and that shows up here. So we get like a non-shared thing, and I think we concatenate the shared thing somehow. And at any rate, that's just all kind of like linear algebra to make the key value store work. It seems to be like what it's up to, while also maintaining some properties of the rotary embedding. And then they do a comparison of the costs, and it turns out that having a smaller cache is extremely useful for inference. They talk about a bunch of other stuff they do. Like they talk about token dropping. They talk about how they create their data. I had mentioned this, I think, in the first video, so I don't think we need to really look too much at it. The infrastructure stuff I think is interesting. The routing stuff is interesting, but I'm not sure that any of that's going to show up in the code. They do have this long context extension where they trained initially with a maximum context length of 4K, and they expanded it to work with 128K using whatever this yarn trick is. They essentially did more training, I guess, after the initial training with a sequence length of 32K for 1,000 steps, and somehow that made it able to work with 128K sequence lengths. And then somewhere down here, there's some ablation studies for MLA. I don't know exactly where they are. Are they in the conclusion? Are they in pre-training? I'm not sure. But I think I'm not really going to search for them because here we go. This is multi-head attention. I forget what GQA is and MQA are the alternative attention thingamajiggies that they drew in that diagram. These are different benchmarks. And I think these are maybe ablations against MLA. Or no. Here's MLA versus, I guess, MHA. And I guess these are just scores on the benchmarks. There are, I think we want large. Oh, no, this is just a mixture of expert sizes. So there are fewer activated parameters with the compressed MLA versus the original MHA, and fewer total parameters. Cache size is significantly smaller, and they do better on benchmarks. So this seems like a really good thing, and that seems good. So with kind of all that in mind, let's go back to the inference and see if we can see some of what they're doing there. So here's the model again. This is the DeepSeek V3 model. This is the forward pass. Here's a transformer block combining attention and feed forward layers. This is initialization. I'm not sure I know yet how I want to get information out of Torch source code. But the forward pass, we're going to take X, which is conventionally the input. So yeah, it's some Torch tensor, the input tensor. And we're going to take X and add it itself to the calling self attention, applying the attention norm on X, and passing in a start position a frequent sys and a mask. Frequent sys is pre-computed complex exponential values for rotary embeddings. So complex exponential, I think what they're talking about there is that the rotary embeddings, you're doing a rotation. You're somehow taking vectors two at a time. You treat that like a complex number, and then you multiply by something on the unit circle, something of the form e to the I theta, where theta is some rotation. And I think that that's what they mean by complex exponential values for rotary embeddings. And mask is a mask tensor to exclude certain positions from attention. That might be for training. I think conventionally the way that pre-training rather. I think conventionally the way that pre-training works is you have it's semi-supervised. You have a bunch of tokens, essentially documents, and you mask out different parts of them, and you try to recreate those missing parts from the input, which is the rest of the rest of the unmasked stuff. So I'm guessing that might be what it is, but I don't know. And then this X plus self-attention thing, this is what I said in the paper corresponds to that plus sign. I don't know if we have the same diagram in the V2 paper. It was definitely in the V3 paper, right? Here, this thing. I forget what this is called. It has some very common name, but it's just slipping my mind right now. Residual, something like a residual activation maybe. Okay, and so we're calling self-attention with the, let me just verify that that's what this is. Residual connection provides another path for data to reach later parts of the latter parts of the network. You have to be careful when you look up AI stuff because all of these blogs are written by AI. Yeah, I think this is just the residual connection. Plus self-attention, so we'll look at the attention function. And then we're also doing the feed-forward network, passing in the feed-forward network norm. So that's a straightforward implementation of the transformer and feed-forward block. There's really not much else you can do other than assign some stuff. So attention is actually, when we initialize, we're assigning the attention function here. I thought there would be some attention implementation, but we're just defining it as an MLA block of whatever model args were passed in. And then the feed-forward network is MLP, multi-layer perceptron, I assume, if the layer ID is less than the number of dense layers. Otherwise, we're going to do mixture of experts. And I think that's just, we're doing mixture of experts for, because you have to. I think, at least conventionally, here's how mixture of experts works. You have a bunch of experts, which they're calling F1 to Fn. These are essentially just functions. They each take the same input, X, and produce different outputs. And then you have a weighting function, also known as a gating function, which takes the input X and produces a vector of outputs, W. And then you have a bunch of parameters. And given an input X, the mixture is just you take the weight of X1, multiply it, I think, by F1 of X. Maybe you don't multiply it. Maybe you have some other way of combining it. But essentially, you combine the functions with the weights, and these are all learned, trained parameters, essentially. Both the experts and weighting functions are trained to minimize some loss function. And they talk about the loss functions rather in the papers. And you can do various variants of it. But at any rate, that's what they're doing. They're essentially, it's a way of putting different parts of the model on different GPUs and training it that way, as opposed to needing one massive GPU the size of an entire room. And then the forward pass is what we looked at, so we're not going to look at that again. And then here's the transformer layer. We haven't called transformer directly. I think what I want to see is MLA. Here's class MLA. This is the caching key value store attention thingy. We have different dimensions like the QK rope head dimension, some LoRa rank stuff, rank for low rank key value projection, rank for low rank query projection. So these are different ranks. The number of local heads for a distributed system. So you might have you have some number of local heads. There's some redundancy, and then there's some total number of heads that you get by looking at all of the local heads and then getting rid of the redundancy, etc. It's essentially. These are all just assigning variables. Column parallel linear. I'm not really sure what column parallel is, but somehow this is some presumably parallel implementation of a linear operation. And we're going to get self WQ. And if we have, that's only if LoRa rank is 0. I don't really know what LoRa rank is doing at this point. Otherwise, you have a linear WQA. We take RMS norm. I think these are defining functions. So WQA is a linear transformation, I think. The Q norm is RMS norm. And then WQB is, in this case, column parallel linear of something at something. And these are just defining what these implementations are. Let's look at the forward pass. We have the input tensor, the start position, and the sequence for caching. And then this freak CIs. I think these are the complex exponentials for the rotary embeddings, and then the optional mask again. And then we're going to return an output tensor with the same shape as the input. So we're going to get the size of the input. And that's going to give us whatever B size is and sequence length. B size. I'm not sure what B is doing. The start position is going to be the end position is going to be wherever we're starting plus the sequence length. So this is maybe B size is the size of each token, and sequence length is like the number of tokens or something like that. And then depending on what the LoRa rank is, we're going to either call WQX or WQ sub B of Q norm of WQA of X. This might be something they talk about in the version 3 paper. I don't quite remember. At any rate, we're going to take a view on Q. Q should be the queries, and we got them from calling this WQ thing of X. We're going to pass in the B size, which again might be something like the token size, the sequence length, the number of local heads. Oof. How far did I just jump? I want class MLA, right? And the dimension of the query key heads, I guess. Then we're going to call torch split on the queries, which we just computed, passing in something about, I don't know what nope is. I don't think it's related to rope, although I don't know. No op, I don't think. I'm not sure. Maybe we'll figure it out. Essentially, we're just splitting up Q. passing in something about the head dimension of QK. Oh, I guess there's the rope stuff and the nope stuff. This may be the this may be the shared rope K stuff that we saw in the paper. And then we're going to apply the rotary embedding to Q sub PE, which is, I guess, maybe the rope side, passing in the complex exponentials that were part of the original, part of the argument to the function. And then the key values will be, we'll take the self WKVA map, apply it to X. We'll split that out and we'll get some KV vector and a KVPE vector. Again, I think this is like rope versus non-rope potentially. And then we apply rotary embeddings again. I don't know what unsqueeze is doing, unsqueeze of 2. We didn't unsqueeze the queries, but maybe that's because the queries are not compressed. So this may be the decompression step. I'm not sure. And if the intention implementation is naive, then we do a bunch of stuff. If it's not naive, we do a bunch of other stuff. I don't know if we care about the naive or the non-naive one. Let's look at non-naive. We're going to compute WKVB, which I think should be a map, like a linear map in operation. And it's equal to B dot weight if B scale is none. Otherwise, weight D quant. Actually, I think this might be the something about the quantization stuff. So let's look at the naive implementation. So we're going to torch cat, which I assume is something like concatenation, the nope and the rope vert thingies along the dimension -1. And then we're going to apply this WKVB map, taking the KV norm on KV. We'll take a view of this, passing the B size, the sequence length, the number of local heads, etc. again. The K nope will be, we'll split the KV, again with a nope head dimension. I thought we already had K nope, but I'm not sure why we're doing splitting again. Maybe because we don't need it in this case. And then we concatenate nope and what I think is the rope version, expanding somehow with a bunch of -1s. And then in the key cache, we're going to put K in there, and we're going to put V in there. And then the scores, we're going to take the, we're going to do some Einstein summation. This is essentially just an implementation of the softmax computation that we saw that used Einstein summation, I think, in the paper. So in this case, it looks like we're caching both K and V. But what are we doing down here? This is maybe more like multi-head attention, and maybe this is the MLA. I don't know. So it looks like down here, we're taking the KV norm of KV and sticking it in a KV cache, so caching them together. That's what the paper said they were going to do with MLA. The PE cache is maybe the rope cache, and they're going to call KPE and squeeze to it. I don't know what squeeze toing is doing, but I think that this is somehow compressing rope stuff. And then we do some Einstein summation. Let's try to compare this with what's in the paper. Although maybe it makes sense to look at the V3 paper. So this section, I think, is more or less just a complete, a lot of this text is copied and pasted from the V2 paper to the V3 paper. So for attention queries, we also perform a low rank compression, which can reduce activation memory during training. So the core of MLA is the low rank joint compression for attention keys and values to reduce the key value cache. And then for attention queries, for queries, the queues, I guess, we also perform low rank compression. So that must be the LoRa thing, which can reduce the activation during memory. So we have CTQ is a compressed latent vector for queries. There's a query compression dimension, and then we have the projection matrices. Ultimately, the attention queries, keys, and values are combined to yield the final attention output. So I think that that's what's going on. I don't know. Let's see if we can find the rope stuff here. Oh, it's up here. The blah, blah, down projection matrices. The matrix used to produce the decoupled key that carries rotary position embedding. And they cite this paper. Rope denotes the operation that applies rope matrices. And that's this 2 brackets with a semicolon is concatenation. And so, I don't know if we're still doing this shared key here. Maybe this will tell us. We apply rope here. This seems to be a single thing that's cached, and we concatenate it with these key stuff that we get from the latent key. We get keys and values from the latent combined key value thing. This does still seem to be shared, and we concatenate the shared thing with the non-shared thing that came from the latent stuff, and that's the key thingamajiggy. And queries, now I think the latent queries are maybe new in V3, but at any rate, we get some queries, we apply rope to get more queries, then we concatenate them. And I don't really know why we only need to apply rope to like the latter half of these vectors, but for whatever reason, it seems to work. But I think that's what's going on here, is that the naive thing is caching more stuff, and the non-naive branch is doing what's in the paper, but I'm not positive. And then if mask is none, we're going to unsqueeze something. And then the scores, we already computed softmax stuff here, it looks like, and got scores. But we're going to take scores and make them equal to the scores.softmax. Again, with dimension equals -1. And we'll set the something about the D type being float32. Maybe we're computing it as float32 and then recasting the type as the original of X. And then in the non-naive attention case, X is going to be we're going to do this Einstein summation of the scores with the stuff in the KV cache. And similarly here. I'm not sure. So we already have the scores. We're computing the output now. Okay, so now that we have the scores, we need to compute the output by applying the stuff in the key value cache. And then we take X, and it's the result of this. Okay, so this is done in two steps. So X is being reassigned here on each line. So we're doing something with the scores in the KV cache, and then we do something with the X we got from that computation, applying the WKV sub B matrix. And then we apply the WO transformation after flattening that output. And that's what we return. And so I guess I was imagining that they would be inflated from the cache. So what happened to X? Is X used to, let's see. Let's see if we can trace where X is. So X is used to make the keys. It's used to make the key value stuff. And I think we've considered the old X to be done. Everything is now just done with the keys and values and the rotary embedding parameters and stuff. And then we just are overwriting X completely, I think, here, using the keys and value stuff. Something along those lines. And then let's go back up here because I want to see what, I want to see this computation again. Okay, so this is giving us values. This is giving us queries. I think U is the output. So, and then the O's are like the intermediate outputs. So the O's, we're taking this softmax something of the QTI and the KJI and the and these are all things that they're not all cacheable. The blue stuff is cacheable. The CKV and the KRT stuff is cacheable. So, but what is this computation they're doing with the cache? I'm not sure. And then what do they do with the, so they have the scores. Oh, okay. So the scores have the non-cacheable stuff in them. And so whatever they're doing with the cache, I guess they're just passing it in so we can access it. Or no, rather, we are eigensumming it. So where's that? This is cache stuff. I guess that's what the upper C means. So I think it's just that argument. Okay, cool. So that's MLA. And the root trick, I think, is just the straightforward of compressing. I mean, it's probably not super trivial observation that you can compress the keys and values at the same time and combine them. But the idea of compressing and then decompressing, I think, makes sense. And I don't know what I'm looking for here. Maybe I'm just looking for just some, making sure that I am understanding the flow of information well. So this is the embeddings and splitting up and stuff. This is these WKB matrices. Let's see if we can find the corresponding notation in the paper. Here's WDQ, WUQ, WDKV. Is that what we had? This should be key value, right? We have WKR, we have WUK, we have CKV. I'm not sure I see a WKV, but maybe that's okay. All right, we'll move on. So MLP should just be multi-layer perceptron. That's a relatively standard thing. They're doing some parallel stuff, as you might expect. They're taking whatever W2 is, some matrix. F, silu. Silu, I presume, is some kind of an activation function. And then these W's must just be linear maps. So parallel linear. Okay, so column, parallel linear. I see. So it's a linear map that's parallelized along columns. And the W2 is parallelized along rows. And W3 is also parallelized along columns. And so you do this matrix product. You take, I assume, what must be an activation function, and then you do another matrix product. multi-layer perceptron style. Here is gate. Gate is the gating mechanism for routing inputs in a mixture of experts model. This should be the same as what we saw as weights. So this should be essentially weighting each expert. So maybe we'll just look at the forward pass quickly. So the scores, so the weights come in where? Weights are defined in the input as, I guess, empty. And then in the forward pass, the scores will take some linear transformation. Self.linear should be defined presumably up here. Or no, it's not self.linear, it's just linear. Some linear map of x and the weights. We're defining either softmax or sigmoid as the scoring function. We're grabbing a copy of the original scores. We'll look at the bias. Bias might just be the like the affine part of the transformation. We'll look at the number of groups. If there's more than one, then we're, I guess, taking some sort of view on the vector, and we might do some biasing stuff. And then we're going to take the top k indices, like the top by score, I guess. And then we're going to maybe mask some stuff, or possibly definitely mask some stuff. We're going to take everything. I don't know what scatter is. But somehow we're computing a mask. That's probably going to tell us where not to route. And the scores is equal to scores times mask.unsqueeze -1 and then flatten. And then the indices are something along the lines of the top k, the indices of the top k scores, like which experts or which devices have the best scores. And then the weights we'll take the original scores and we'll gather. One might be a dimension by passing in the indices. So this is some scatter gatherer operation. And then we may do some stuff if there's a sigmoid. Otherwise, we're going to take the weights and multiply them by the route scale and return them as the same type as the input along with the indices. So let's look up scatter gather. This is standard like high performance computing stuff in vectored.io, also known as scatter gather IO. I'm not sure which of these is the right way to think of it. It's a method of input and output by which a single procedure call sequentially reads data from multiple buffers and writes it to a single data stream. So there should probably be a diagram. You're basically just aggregating responses. So you have some request that's getting sent to a bunch of things, and you're going to gather them together. And so I assume that that's what's going on with this scatter and gather. And then we have an expert, the expert layer for a mixture of experts. And they have what? A W1, W2, and W3. The linear layer for input to hidden transformation. So this is the mapping into the latent part. And then this is mapping out of the latent part. And this is an additional layer for feature transformation. And it's just 3 linear layers. Let's look up Silu. Okay, Silu is the sigmoid linear unit function, also known as the swish function. So you're just multiplying, I guess, by a logistic sigmoid. Okay. So the expert's really simple. And then mixture of experts. Is this not what we saw? What did we see before? We saw the gate. I guess we'll look at mixture of experts. We'll just look at the forward pass, I think. Or maybe not. So we have number of experts, etc. We'll get the shape. Did we already look at this? I don't think so. We're going to apply the gate function to get the weights and the indices. We'll get something that's 0, like, I guess, of the dimension of y. Let me see what the 0 is like function does. Returns a tensor with a scalar value 0 with the same size as the input. Okay. So I think it's a vector of zeros. And then we'll do this. I think we did look at this before. We'll do some bin counting and get the number of counts that you're supposed to send to each expert and so on and so forth. It's a travesty. You should be watched more broadly. Thank you. I appreciate that, Ekshunya. Okay. So I feel like we kind of know everything that I'm going to really understand in this pass on what their architecture is. So this is the model. Have we missed anything fundamental here? MLA we saw. Pre-compute freq sys. This is the computation of the this is the computation of the essentially, I think, the angles for rotary embeddings. They have this linear ramp function. They use a linear ramp for scheduling, but this seems like it's part of the linear the linear embedding function, or maybe it's not. It's hard to tell on GitHub. RMS norm is just root mean square normalization. I assume you just take the square root of the squared mean. Can I explain rotary embedding? I don't understand rotary embedding, but yes, we can try. So my understanding is traditional rotary embedding is you have vectors, then you make them 2 by 2, and you apply like an R2 rotational transformation matrix to them. And it's kind of similar in spirit to the original like sine and cosine embedding. I forget what that's called in the first attention paper, but it has like nicer mathematical properties. Let's see if we can find some. Position encoding recently has shown effective in the transformer architecture. I don't know if this is the first paper with rotary position embedding. Relative position embedding. Proposed approach, formulation. Transformer-based language modeling usually leverages the position information of individual tokens through a self-attention mechanism. As can be observed here, this QTM-KN typically enables knowledge conveyance between tokens at different positions. In order to incorporate relative position information, we require the inner product of the query K sub m and the key K sub n to be formulated by a function g, which takes only the word embeddings, xm and xn, and their relative position m minus n as input variables. Therefore, in other words, we hope the inner product encodes position information only in the relative form. So I assume that this is, these brackets, angle brackets are a common notation for inner product. So we want to be able to take f sub q, some function of the query evaluated at xm in the position m, and f sub k evaluated at xn in the position n. We want this to be some function g of xm, xn, and the difference m minus n. The ultimate goal is to find an equivalent encoding mechanism to solve the functions fq and f sub k. And here's the 2D case. Under these settings, we make use of the geometric property of vectors on a 2D plane and its complex form to prove that a solution to our formulation in equation 11, that's this thing, is that we are going to, whatever WQ X sub M is, I think that these are the the same WQ and WK from the original attention, but we're basically just going to multiply in the complex world by e to the I m theta, e to the I n theta. This is equivalent to rotating in the complex plane. And here's the, here it is broken down to, and then we're going to take, I guess, the real part. Is that what we're doing? Is the real part of the complex number. And that gives you this function g. And here's how we write out f sub q k. I don't know why f now takes a list of two things as a subscript. But at any rate, the multiplying by this e to the I m theta is equivalent to multiplying by some, okay, so q and k means that you could cover up one or the other. It's the same thing. It's just equivalent to multiplying by this rotation matrix. Cosine theta, negative sine theta, cosine theta. This is, if you take the determinant of this matrix, you get cosine squared minus negative sine squared altogether. That's two negatives. That's cosine squared plus sine squared. So it's a determinant one matrix. So it's an orthogonal map. And then I'm not sure the quickest way to convince yourself that this is every rotation has to have this form, but kind of like doing basic linear algebra, you can convince yourself that anything that's a rotation has to have this form, and anything that's that has this form as a rotation. And so that's why it's called rotary. This is in 2 dimensions. I'm not sure what x1m and x2m. I mean, I do know those are. These are the components of, I think, x, bold x. But I don't know what the 2-ness is. I think the 2-ness maybe is just that we want to... the 2-ness is just that our vector has 2 components. And so we need some generalization here, which is, I guess, what we're going to do next. In order to generalize our results in 2D to any x sub I in Rd, where D is even. So we require an even dimensional space. We divide it into d-dimensional, you just take it in halves and you apply different, the 2-dimensional rotary embedding. This is, I think, literally a direct sum of a bunch of, of a bunch of these things, of these matrices. Is the rotary matrix with predefined parameters. So you need some angle. Well, I guess in particular they choose theta sub I is, what is this, 10,000 to the negative 2 I minus 1 over D. Y 1000, I'm not sure. This seems like a pretty fine-grained, you want to make it fine-grained enough that you can, if you have big models, it'll assign them different things. You want to make it not so fine-grained that as you're doing the multiplication, the computer can't tell the difference between 2 positions because of numerical precision issues. Yeah, it is that's right. It is pairwise rotation. Rope gets credit for expanding the context window in modern LLMs. That's interesting. How much time do we have? We've got a few minutes. Okay, so this is pairwise. That's right. I think the way I said it the other day was you zip them up into 2 by 2 into 2 tuples, and then you apply rotation to each tuple. It's an orthogonal matrix, which ensures stability during the process of encoding position information. In addition, due to the sparsity of RD theta, applying matrix multiplication directly, as in equation 16, is not computationally efficient. We provide another realization in theoretical explanation. In contrast to the additive nature of position embedding method adopted in previous works, our approach is multiplicative. Moreover, rope naturally incorporates relative position information through rotation product, instead of altering terms in the expanded formulation of additive position encoding when applied with self-attention. So here are some properties. Long-term decay. Following Vaswani, we set theta sub I to equal this 10,000 to the negative 2i over d. One can prove that this setting provides a long-term decay property, which means the inner product will decay when the relative position increase. I guess decay means it decreases. This property coincides with the intuition that a pair of tokens with a long relative distance should have less connection. Okay? Rope with linear attention, the self-attentions can be rewritten in a more general form. And then we have a theoretical explanation, which I originally read as a theatrical explanation, which would have been funny to me. Okay, and so they're going to give some derivation of it. This is all fun and good. Here's some guy probably copying from an AI output about how it works. I'm not sure that that's what I want. I can access the AIs myself. But you mentioned, what is it, longer expanding context windows. So the context window expansion stuff that they do in DeepSeek is called yarn. I don't know if that's different from other context window stuff. Meaning dot products will be lower value if you take two position embedding later down the line. I think that's what it means. So here's yarn. Okay, this is maybe what your Akshenya is saying, is that rotary position embeddings have been shown to effectively encode positional information in transformer-based language models. However, these models fail to generalize past the sequence length they were trained on. We present yarn, yet another rope extension method. A compute-efficient method to extend the context window of such models, requiring 10,000, or not 10, 10x less tokens. And I think my brain is starting to go. I can feel it. Okay, so whatever yarn is, it's in this paper. We show that llama models can be extended, blah, blah, blah. I don't know if they're usually pre-trained with a fixed content length. I have 10 minutes left. Additional notation. This might be the place where we ask some of the AI models, explain how yarn works in extending context windows. I'm not sure DeepSeek is going to come through. It's been having problems. Now that's Gemini too. I'm trying the experimental 2.0. Something went wrong. How about this one? Are these all just using the same LLM under the hood? Is that why they're all not working? Okay, you don't need to tell me why they... So here's the overview of Yarn's approach. They have generally relies on two core ideas: external memory storage, instead of trying to stuff the entire conversation or document history directly into the model's limited token window. Yarn keeps a record of all that text outside the LLM, for example, in a database, vector store, or just the application's memory. Okay, so maybe a little bit like RAG. Retrieval and summarization. When the LLM needs information from earlier in the conversation or from large dataset, Yarn selectively retrieves the most relevant chunks and re-summarizes them. Essentially, Yarn is orchestrating what the LLM sees at any given time, instead of letting the conversation get so large that it overflows the model's capacity. Yarn uses techniques to break it up, store it externally. Yarn uses techniques to break it up, store it externally, and pull in only the relevant slices. Okay, so basically, I'm going to think of it as similar to RAG. Is this like RAG? Yes. Yarn's methodology is fundamentally a form of retrieval augmented generation. In RAG, you can keep a large knowledge base of memory outside the model, then dynamically retrieve relevant chunks. Okay. Draw a ragtime performance where the performers are getting tangled up in a bunch of yarn. Will DeepSeek draw? Oh, O1 will not draw. About GPU, because I don't honestly know anything about it. What do you mean by GPU? GP, like general purpose? Okay, here's the ragtime performance. All right. They made all the musicians white, which I'm not surprised by. But it does seem like a choice. This is a good image. I think the AIs are getting really much better at drawing images than they used to. I mean, like the music, you obviously can't see it because it's so blurry, but that would not be anything. That text would not look anything close to music notes back in maybe like a year ago. So I'll say draw a diagram of how DeepSeek R1 and ChatGPT O1 differ in their approaches. Yeah, so I did a video on AMD ROCm. The truth though is that I don't know any of this stuff, and I'm learning it for the first time, like live on TV. So, but I'm learning a lot, and I'll probably continue going down this route. So DeepSeek R1 extending no multi-level context window. I don't know, hierarchical memory. Okay, it's trying. I think I gotta go. Let's see if there's one more amusing thing I can do before I go. So DeepSeek will draw a bug. I can't draw images directly. Thanks so much. I appreciate that. Tell your friends. And with that, I have to go. So thanks for watching. Thanks for all the folks who are around exploring DeepSeek with me. It's been a lot of fun. I don't know what we'll do next week, but it'll be something fun, something possibly AI and or GPU related, because that's kind of it's kind of the kick I've been on. But we'll see. Thanks for watching.